All right, line A1, learning task 9b. At this point, we're just going to continue on in the inductors in DC. I just split the videos apart because really what's happening is we're kind of changing tack at this point. We've covered the basics of an inductor, the fact that it opposes any change in current, and that it does through the use of voltage developed off of magnetic fields. And then it jumps into this whole other section that's going to start to talk about what's referred to as mutual induction. Mutual induction is going to go and be a basis that we're going to build a lot of our other machines from. We're going to go and build transformers from it. We're able to go and pick up voltage on one side and pass it over to the other. We're going to go and build motors from it. We're going to pick up voltage on one side, pass it over to the other side, develop current and develop torque off of it, and a whole pile of other components that are all going to happen through this, which is why I want to treat it as a separate type of video over here. Let's take a look at what's happening inside of this picture over here. First of all, they're showing mutual induction between two coils that are close to each other. If I have got a changing value of current inside one of these, okay, we're just going to go and take a look at this one and say that this current is going up right now. If that current would be going up, that would mean that I would have an increasing size of magnetic field, which means that its magnetic field is going to be exiting, so it's good. Based upon whichever one of these is going to be the north and south. Normally what we would have is we would have a magnetic field that is just going to go and loop through looking something like that. But as soon as we bring something else close by, my magnetic lines don't want to go through the air if they can help it. They want to go and take the path of least reluctance, so they're going to go and stretch a little bit so that they can then take the easy path through another coil over here. So over here, as I increase my amount of current, I'm going to go and see an expanding amount of magnetic fields. Those magnetic fields are going to go and hit this core over here. That's where they're going to get attracted to. And then they're going to be expanding inside of here and cutting out through those conductors on the outside. As they cut out through those conductors, we've got everything that we need to go and establish voltage, right? EG is equal to BLV. I'm going to have a flux density. That's going to be the flux itself. I've got a length of wire. It's coiled around here. I'm going to have velocity, how quickly that flux density is going to be moving out of this. Now what we're showing over here, holding one coil close to another coil, isn't going to be our most effective way of gaining mutual induction, because we're going to go and deal with what we refer to as fringing. Fringing is where I'm going to go and have some of my magnetic lines of flux that are going to bow out and push around. We're also going to have some complete lines of flux that are just, because this thing is going to have a certain number of lines of flux, it's too much work, and they're going to go around like this. What we can do is we can confine the flux lines by putting them across onto a single coil over here. And when we place them onto a single coil like this, what we then do is we go and hold onto all of these lines of flux, or on top of a single core, I should say, not a single coil. That core is going to go and maintain all of our magnetic lines of flux together. That way we're going to be having almost all of the lines of flux that are created on this side that are going to cut through on this one. So we're going to have a very efficient transfer of voltage from one side to the other. Here's how it works. They're going to show it to us here inside of a little DC supply. The instant that we go and close this over here, we are going to go and have on this side, this is going to see this coil as a inductor, and we are going to go and have a rising value of current. That rising value of current is going to go and cause us to have a expanding magnetic field. So that's expanding magnetic field. That is also going to be traveling through here, and it is going to be expanding outwards. It's going to be pushing out against those other windings over there, cutting through them. Because it is cutting through these, because we're creating that expanding magnetic field, because it's cutting through these, at the instant that we go and turn this thing on, we are going to go and have a little bit of voltage. Boom, it's just going to go and happen. Then once this thing reaches steady state over here, like that, then I'm no longer going to have anything that's going to be cutting on this side. I'm still going to have magnetic lines of flux, but they're not expanding out or contracting back in, so there's no relative motion between those magnetic lines and between the conductors themselves, which means that we're not going to generate any voltage, right? Once again, EG is equal to BLV. If we don't have any movement, we don't have any velocity. If that value is 0, my generated value of voltage is going to go and be 0. So right now, when I am at steady state on my supply side, I'm not going to have anything induced on the other side. When I go and drop my voltage on the supply side, what I'm going to have is I'm going to have those lines of flux which have been pushed out, which are now going to cut back in. And as they cut back in, they're going to be cutting in the opposite direction. Before they were expanding, now they're cutting back in. And because they're cutting back in the opposite direction, it's going to induce a voltage in the opposite sort of direction. So what we have, I'll just change this one to red, is that the instant we close the switch and we see an increase in current, we're going to have voltage in one direction. When we have got the current at steady state, that's the green, we're going to have no voltage on our secondary side. And when I go and collapse, when I shut off this supply over here and collapse those lines of flux, I'm going to have voltage in the opposite direction over here. We'll refer to these as being a primary side and a secondary side. The primary side has got nothing to do with what's high voltage and what's low voltage. Primary just means that's the side that we are feeding electrical power in. The secondary side is going to be the side that we are taking electrical power back out of these. And it actually goes through a bunch of really fantastic changes on the way to get there. Really, what we're seeing is we are seeing this change from electrical energy to magnetic energy, and then from magnetic energy back into electrical energy that we are going to go and have. Or if I were to be a little bit more pointed about it, I could say that this side over here is an electrical load, but a magnetic source. It's an electrical load taking current in, but it creates a magnetic field, so it's a magnetic source. This side over here is a magnetic load. It leaches off of that magnetism, and when it does so, it generates value voltage and becomes an electrical source. Remember, for every action, there's an equal and an opposite reaction. If one of these is going to be an electrical load and magnetic source, the other one's going to be a magnetic load and an electrical source off of these. They are going to go and have what's referred to as mutual induction, and the mutual induction is going to be measured in henries as well. It's got the same sort of formula that we are going to go and have. The value of mutually induced voltage is going to be based upon M, negative M, delta I, it's missing that delta, over top of delta T, that we are going to have the change in current over top of the change in time that we are going to go and have. So it's very similar looking, just now we're using that M to go and indicate that we have got mutual inductance. The better the core that we have linking these two, the better the mutual inductance that we are going to go and have. Where do we use this? Well, what we had over here is what we refer to as a pulse transformer. It's not being used as a transformer because it's a DC supply over here. We'll cover transformers later. It is transforming, but it's only transforming on the shoulders. In other words, we only get voltage out either when it's rising or when it's falling. So on this side over here, we're only getting any sort of recognizable signal at those points. So we can use it to go and pass through a pulse when something turns on, or we can use it to pass through a pulse when something goes and turns off. We're also going to go and be able to affect the values that we're going to take out of these sides by changing the number of turns that we're going to go and have. If I have got more turns on this side, let's go and add in a few more turns onto this winding over here. What that is going to do is it's going to go and change this formula. EG is equal to BLV. We have not changed the flux. That's still coming from this side. We haven't changed the velocity. That's still going to be based upon how rapidly that line of flux is expanding. But what we have changed is we have changed the length. And if we bring this length high up, then it's also going to go and bring our generator value of voltage high up. This is how transformers work at, a very granular sort of level. We just have differing numbers of turns on one side versus the other, which are going to go and give us differing values of voltage based upon flux linkage that we are going to have. There is a formula. The formula is going to go and talk about, this later on, but it's going to say that, my E, I can't draw, that's another E secondary over top of E primary is equal to my NS, that's an NS over top of NP, the number of turns over top of my primary, etc. In other words, what I can do is I can cross multiply this EP up to this side over here so that I can have a formula that will then look like ES is equal to, let's write that out one more time over here, is equal to EP times NP over top of NS that I'm going to go and have. Or sorry, ES, mixing these numbers up here, NS over NP. That's the way that formula was before, and we just, moved these ones out and across there. This is going to allow us to go and pick up values of voltage and carry them over. And what they show us is a DC system where we are going to go and create ignition. So one of the useful points that arcs can do for us is to go and create this ignition where we are going to go and have current that is going to be fed into one side and it's going to get opened and closed. So if I take a look at this, a couple of things I want to note. They show ground off of these. Anytime that they show ground, you can just physically draw a line from component to component to show that those two are connected. So I'm just going to draw that right there, like that. I've got what's referred to as a distributor point. This is a little bit of automotive, but it's old school automotive over here. I've got a distributor point that's going to be based off of a cam. This cam, as it rolls out, pushes that thing open, then allows it to close, pushes it open, allows it to close, and that cam is going to be synced up with my rotor. So it's going to go and open and close at the same time as these are passing, what we refer to our distributor cap. What we see, if I follow my path of current through here, is that if I have got current, if I close that ignition switch, I'm going to have current that's going to travel through here. It's going to go and travel through here and back down into here anytime that that switch is closed, which is great. We want to go and have that. So anytime that that switch is closed, I've got that current that is going to go and travel through there. But then anytime that that switch goes and opens, this is going to try to maintain that direction of current that was traveling through. This opening and closing action is going to go and induce values of voltage inside of our circuit. And this is where we're really going to go and see these circuits trying to go and maintain. When this opens over here, it's going to go and collapse its lines of flux that it generated onto itself really, really rapidly. As it collapses those lines of flux are going to go and cut through these coils over here. They show them separated, but they're going to be wound together. And so what we'll have is those lines of flux that are going to be collapsing back in onto these. Because they're collapsing back in so rapidly, trying to go and maintain current over top of my distributor points over here, what happens is they are then going to go and create massive amounts of voltage that are going to be picked up by this side over here. Because this side has got more turns, so therefore more turns, e.g., is equal to beta, length, and velocity, right? Lots of turns means I'm going to go and get a high value of voltage that's going to be established out of here. As these collapse back in rapidly, inducing a large amount of current, that current gets picked up on this side and gets changed into a super high value of voltage through these number of turns over here, which is then going to go and shoot across this little arc over here, or shoot across a little gap there, creating the arc. Now, we're not too concerned about this drawing overall because it's describing an automotive ignition system. They're just showing how we can open and close these circuits, and when we open and close them, how that's going to go and give us a useful component out of our sparks. We will use these inside of oil and gas. We've got a lot of like flare stacks and things like that where we have to burn off, rough gas and things. We will need to have them for that, as well as for a lot of our gas-fired appliances, even household hot water tanks and boilers and things like that, as well as a lot of our industrial equipment. Be very careful anytime that you're working on gas-fired equipment. The gas can turn on and catch fire, which obviously you don't want to die in a gas fire. But if you're working around it, even with the gas off, and you accidentally trigger one of these circuits, you're going to get an incredibly large amount of voltage that's going to go and hopefully not get passed over you. But if you're close enough by, you can definitely arc it over top of yourself. Okay, at the very bottom of the page, underneath this picture of the simple auto ignition system over here, they then go and have one tiny little paragraph that's actually really critical. It says, not all of the values are the effects of mutual inductance are desirable. The wires of communication circuits often receive interference in the form of voltages induced in them by changing currents in other circuits placed nearby. If you've done any sort of residential wiring where you're pulling in the low voltage, the Ethernet, the data, tel, all that stuff, you know that you got to keep that separated from your line values of voltage. The higher the value of voltage, or the more critical the low voltage system is going to be, the further away you have to keep that separated so that you don't end up with interference. Interference is a really bad thing because what we get is we just get magnetic lines that are going to be picked up from one to the other, two conductors in parallel. If I've got a lot of current passing through here, it's going to cut across this conductor over here, induce values of voltage, and all of our digital signaling is done through values of voltage. Keep them separated, okay? That's it.